compare these two solutions, one with a lot of buffer, one with just a little. The first thing we're supposed to do is compare the pH of these two solutions, and whenever we have buffers, probably the go-to equation is Henderson-Hasselbalch. Now, notice that in both of these solutions, we have the same amount of acid and conjugate. So in the Henderson-Hasselbalch equation, this value of concentration of conjugate base over acid is 1. And when we take the log of 1, we get 0. So the pH is the pKa for both of these solutions. So we basically just need to find the pKa of ammonium. The Ka is given, the pKa is the negative log of that, so I just put in negative log of 5.7 times 10 to the negative 10, and we get 9.24. Alright, so now what we have to do is add 1 liter of 1 molar strong acid to both solutions. And something to notice is that we have exactly 1 liter of these solutions, so in that unique circumstance, we can say that the molarity is also the number of moles. So we're effectively adding 1 mole of hydrobromic acid. What is that going to do? What reaction are we going to see here? That's going to react with a base, right? Because hydrobromic acid is a strong acid. And the base present is ammonia. And basically this H plus is going to transfer to the ammonia. And look, we're going to get more of our conjugate acid. And since this, the stoichiometry for this reaction is pretty simple, it's all 1-to-1 ratios, right? So we use 1 mole of this, we use 1 mole of this, we make 1 mole of this. So for solution 1, let's think about where we end up. We started with equal amounts of ammonia and ammonium, and we lost a mole of ammonia, we gained a mole of ammonium. We now have a 1-to-3 ratio of conjugate base to conjugate acid. And it's that ratio that's important in the Henderson-Hasselbalch equation. Technically, we have to put in the concentrations of ammonia and ammonium, and since we combine solutions, we have more than 1 liter now. So technically, let's look at our concentrations. Molarity is moles per liter. We have 1 mole of ammonia and a total of 2 liters of solution since we combined 2 1-liter solutions. So we get 0.5 molar for our ammonia, and we're also going to divide by 2 liters here to get 1.5 molar for ammonium. If you forget to do this step, it's usually going to turn out all right, because, like I said, it's the ratio of base to acid that's important, and your ratio of moles is never going to be different than your ratio of molarity, because the volume of the solution of the base is the same as that of the acid. But anyway, I'm going to go ahead and put the pKa in here, and then plus the log of that, 1/3, or technically the 0.5 over 1.5, which is, we know that's the same as 1/3. And log of 1/3 is negative 0.477. And there we have it, a pH of 8.74 after you add a bunch of strong acid. So, yeah, it made the solution a little more acidic, but it's still a basic solution. Its pH is still over 7. So the buffer pretty much worked. But what about in the situation where we add the same acid solution to a buffer with less buffer, solution 2. So what happens here? The HBr, the hydrobromic acid, quickly goes through the half a mole of ammonia present. So we do react half a mole of the bromine with that half a mole of ammonia, but we're out of ammonia then. Everything present is now ammonium, the conjugate acid. And even after we run out of ammonia, we still have half a mole of hydrobromic acid left. So essentially what this pretty much becomes is a solution of hydrobromic acid. And we know that's a strong acid. So the hydronium ion concentration is going to be pretty much the concentration of hydrobromic acid. And so if we know that, then we simply use this equation for pH. Negative log concentration of hydronium. And drumroll, we find a pH of 0.3. So this is the pH of a very acidic solution, which is what we expect because we're basically left with a solution of HBr, right? So definitely not basic anymore, very acidic. So we have broken the buffer since we added more acid than the conjugate base that was present.